Hello and welcome to our physical sciences session. My name is Temba. Today we are focusing on our attention on understanding the chemical formulae of substances, which is, one of the aspects that has to do with chemical change. So for us to be in a position to actually understand what happens in a chemical reaction, first of all, let's try and create an understanding of the actual substances that take part in chemical reactions. So as a result of that, we shall focus our attention for the purpose of this session on the chemical formulae. Now let's try and locate chemical formulae within the broader, section of quantitative aspects of chemical change, which has to do with reactions, of course. Right. Now, from the concept map, there is our chemical formulae, okay? There is no way that we can talk chemical formulae without making reference to the periodic table of elements, right? Okay, so the periodic table consists of elements. Okay, from these elements we can talk about compounds. Then from compounds we understand the molecular formula in terms of percentage composition as well as empirical formula of the substances that are involved, right? So these are the three aspects that we shall focus our attention for today as part of this session, right? Now, the big thinking question that's going to guide us in our discussion is, have you ever thought about how can we tell what quantity or amount of each element is found in a compound, right? First thing first, let's break it down. What exactly do we mean by a compound? We're talking about a substance that consists of two or more elements of different types that are chemically bonded together. So in terms of composition, we want to understand exactly how each of these elements contribute in terms of mass, in terms of percentage to the entire compound. So the question, that's why it's phrased as, how can we tell what quantity of each element is found in a compound, right? Keywords, very, very important in terms of definitions. Our point of reference then becomes our examination guidelines. Remember to capture the keywords in the correct context. So it's an all or nothing type of an arrangement, and it tests, when it comes to definitions, it has to do a lot to do with our remembering or our basic recall. So we need to remember the keywords. So some of the terms that we'll use once too often in our discussion for today are as follows. We'll talk about the molecular formula. How is it different from empirical formula? So these two are types of formulae that describes compounds or substances, okay? Then we'll talk about percentage composition, cation and anion, amongst a host array of others, but these are the ones that we shall be using once too often than others, right? Okay, now in as far as chemical formulae, from what we already know is that matter consists of particles, and these particles are actually elements. Elements are made up of atoms. But if we zoom our attention to the elements, we talk about the periodic table of elements now, which has a lot to do with the classification of substances or elements that are found in the periodic table. So there are three main categories, okay? We've got metals, metalloids, and non-metals. So metalloids, sometimes we refer to them as semi-metals. Okay, now if we can draw our attention to just the periodic table, at some point we would have maybe looked at the first 20 elements, but in its entirety, the periodic table, this is a typical example of the periodic table as we know it. Okay, so the substances or elements that are listed in the far to our left, this column, which is blue in color, represents the metals, okay? So we've got alkali metals and alkali earth metals, okay? And then in the middle, where we've got these are our transition metals. So anything that we've circled falls under metals, but there are different categories of metals. We've mentioned that groups are actually the vertical columns and periods are actually the horizontal rows. So metals will be further broken down into different categories. And then we've got metalloids, which are actually, semi-metals. These elements, just to mention a few, like silicon, they've got both metallic and non-metallic properties. Hence we call them metals, metalloids or semi-metals. So the word semi metals, it means they do show some metallic properties, okay? So the word semi-metals and metalloids can be used interchangeably to refer to the same category or classification of elements. And then further to our right, we've got non-metals, okay? These are elements like your bromine, chlorine, you name them. But our focus is not basically on, it's not actually on the periodic table, but it's on the chemical formulae, okay? So a chemical formula, what does it tell us? It gives us information about the chemical proportions, okay, of atoms making up a substance. A substance could be a compound which consists of, two or more elements that are chemically bonded. It could be a molecule of an element or a compound. So a molecule could either be an element, okay, or it could be a compound, right? You immediately recall that when we talk about molecules, these are covalent substances, okay? We can talk of diatomic molecules like oxygen. We can also talk about compounds which consist of different elements that are chemically bonded together. Or it could be ions. We can talk about ions, a formula of an ion like Na+. We can talk about Br-. These are ions. So formulae, chemical formulae can be used to represent any substance, okay? Right. And then furthermore, the chemical formula makes use of symbols, okay? So these symbols, we actually talk about the chemical symbols as we have seen in the previous slide, that when we say Na, we're referring to the sodium ion, Br, the bromine ion, O2, the molecule of oxygen, H2O. So these are the symbols that we use to refer to specific substances, okay? But amongst those, we can talk about numbers. There can be parentheses, dashes, commas, pluses, and minus. For argument's sake, we can talk about ion 3, okay, oxide, okay? Immediately, this is a chemical name, okay? So the 3 is the number that we talk about. But if we talk about the formula, we can also talk about Fe2O3, something like this. So these are the numbers, these subscripts that we talk about, They can be brackets, they can be dashes, just to refer to specific substances. So each element has a unique name as it is reflected in the periodic table of elements. Now, if we focus our attention a little bit on the actual naming of compounds, okay, remember, when we talk of compounds, it means it's now understanding that in the periodic table, there are individual elements. Now, when these elements combine with each other and form compounds, it means these compounds are essentially composed of elements or atoms of different elements that are bonded to each other. Okay, so, but in a compound, these, the constituent elements are reflected in both the chemical formula and name. Say, for argument's sake, we can talk about an ionic compound that consists of two components, which is a cation that is positive and an anion that is negative, okay? So each one of these is derived from an individual element. So in the ionic compound, you'll have both elements represented in the name of that particular compound. So some substances have common names in their actual chemical names. So there are isolated cases where we would have a chemical name as well as a common name. All right, we talk of salt every day. That's a common name. Caustic soda, we talk of lime. These are common names, but these common names are actually related to specific chemical formulae. Okay, so a chemical formula essentially shows the chemical composition and proportion. So the big idea about the chemical name is that it also tells us the composition, or in terms of what elements make up that compound. Okay, so the name in itself, it would be reflective of the names of the elements that make up that particular compound. Okay, take for argument's sake, sodium and chlorine. We talk of sodium chloride. So in that name, it captures the two, constituent elements that make up that particular compound, just as an example. Okay, right. And then let's look at a simple activity like this one, which says, first of all, in the first column, we've got the name. followed by the formula, and then what atoms or elements make up that particular compound. Okay, so carbon dioxide, the formula is CO2. Okay, what does this CO2 tell us? It tells us that this substance consists of carbon as well as oxygen. All right, now the dioxide suggests that there are 2 atoms of oxygen and then 1 carbon atom in this formula, right? And then now we've got 2 hydrogen atoms and an oxygen. Okay, in that order we assume. So we've got 2 hydrogen atoms and oxygen. Okay, so the common name for this will definitely be what? Water. Okay, so in that chemical formula, we can immediately pick up that for a formula unit, in this case, a molecule of water consists of 2 atoms of element hydrogen and a single atom of element oxygen. And then we have got the third one, which is ammonia, NH3. So in terms of composition, there is a nitrogen atom. So 1 atom of nitrogen, okay? And in this case, 3 atoms of what? Hydrogen, all right? That's what it says. And then from this formula, we are able to work backwards and actually determine the name of the substance. Okay, this substance consists of 1 copper atom, right? And then 1 sulfur atom, and then 4 oxygen atoms, okay? Right, so the name of the substance is copper sulfate, right? So that's the name, okay? And then calcium hydroxide, okay? The elements that are present here is calcium, hydrogen, and oxygen. So calcium hydroxide, Ca, that's the symbol of the cation, which is positive, which is calcium. And then the hydroxide ion is a polyatomic ion. Okay, then there's a 2 there, okay? We'll discuss as to how exactly we arrive, but our focus is if we are given this chemical formula, we are able to say there is 1 calcium atom, okay? This 2 suggests that it's for everything in brackets, which is for the hydroxide anion. And then what do we have? 2 oxygen atoms, okay? Right, that's oxygen, all right? And then what else do we have? We've got 2 hydrogen atoms. Okay, so that's the gist in terms of composition, right? Okay, and then in naming ionic compounds, these are some of the rules. The metal cation is derived from some element, okay? And then elements on the left-hand side, will identify them to be, the metals, okay? So these metals, in most cases, they actually form cations, which are actually positive, okay? And then, so when we name these elements, we start with the cation followed by the anion. So in some cases, there will be terms like mono, meaning 1, di, meaning 2, tri, meaning 3, and so on. So these are some of the common features in naming substances. Then when we talk polyatomic ions, we're talking about ions that have got more than 1 element, and they always consist of the same ratio of elements as a group. Say, for argument's sake, these 3 compounds, ionic compounds, this is sodium sulfate, okay, calcium sulfate, aluminium sulfate. There's something that is very common in these ionic compounds, is that all of them are sulfates, okay? Now, from this, how did you arrive at that? Why are we saying that they are sulfate? Because all of them, they contain this polyatomic anion. Polyatomic, it means it consists of more than 1 element, okay? So this polyatomic ion, in this case, which is common, is SO4 2 minus, okay? Now, there is SO4 2 minus, SO4 2 minus, SO4 2 minus. So they consist of the same ratio in that for every sulfate anion, there's 1 sulfur atom and 4 oxygen atoms, okay? And the net charge in that polyatomic ion is 2 minus or -2, whichever way you choose to actually refer to it, right? So when writing the chemical formula of an ionic compound, you start with the cation followed by the anion. So if we've got that sodium ion and the chloride anion, Okay, we always start with the metal followed by the non-metal. And the main idea is that at the end of the day, these charges must cancel each other out. So if you realize it's Na plus 1, Cl negative 1. So we can put them in that order, metal, non-metal, then it gives us an ionic compound, as long as the net charge actually cancels out or works out to 0, whichever way you choose to look at it. So this will be just NaCl, and the name sodium chloride suggests that it consists of sodium and chlorine. But take note of the suffix IED, which is the chloride, okay? And then once again, we are given the different ions, okay, below. We want to write down the formula of compounds, okay? These are different cations. These are cations, okay, because they are positive. And then these are anions because they are negative, okay? Right. Now, potassium bromide, okay? That's our potassium anion, bromide. Do the charges cancel out? Yes, of course. So it's KBr, okay? And then calcium bromide, where is calcium? There is calcium, okay? Okay, and then the calcium carbonate, where is the carbonate ion? This is a polyatomic ion, okay? So calcium carbonate, calcium is 2+, and then the carbonate has a charge of 2-. So that works out. So we would remain with CaCO3, okay? So first is the cation, followed by the anion, okay? And then ammonium carbonate, the ammonium ion, there it is, okay? That's our ammonium ion. And then the carbonate is actually 2-, all right? For every carbonate, we must have 2 of these so that it cancels out, okay? So at the end of the day, we'll start with the positive one, which is NH4, okay? We need 2 of those, okay? And then CO3, okay? So that's our ammonium carbonate, okay? Hope that makes sense. And then the last 2, iron 3 oxide. Of particular interest to us is this 3. This suggests something about this transition metal, that it has got a charge of 3+. So this is the ion that we are talking about. So that's the ion 3 that we are talking about. But the oxide is 2-, okay? So in this case, we've got Fe 3+, okay, and O 2-. So for these to cancel each other, we can actually cross them and get Fe, we take the 2 there, and then O, we take the 3 there. So this is iron 3 oxide, okay? In this, there is iron and oxygen. These are the 2 elements in terms of composition. But there is 2, the ratio is 2:3, right? And then last but not least, we've got copper 2 sulfate. That's our copper 2. And then that's our sulfate ion, okay? Now, the 2- cancels out the 2+. What do we have there? We start with the positive according to our rules. We'll say Cu and then SO4. Okay, so that's as far as the main idea. But the chemical formula of an element or a compound, it gives the ratio of moles of each element in the substance. So the main idea is that given the chemical compound or the name suggests the chemical composition in terms of what makes up that compound. But then if we look at the chemical formula, it gives us an idea of the ratio of moles of each element that makes up that compound. Having said that, let's take a short break as we'll continue to explore percentage composition in our second segment. Let's take a short break for now.